Good afternoon, everyone, and welcome to section 5.2. This section is all about the normal distribution. So we've looked at bell-shaped curves quite a lot. They have that characteristic bell shape that we've been looking at, where they are both unimodal and symmetrical. And we'll see later why this shape is so common. But for now, we're just going to say that you can see this distribution whenever your continuous random variable is a result of many chance outcomes. Now, you can continue to call this a bell-shaped curve, but statisticians call this the normal distribution. And there's another term for it as well. If you're in physics, it's often referred to as a Gaussian, but we're just going to go ahead and call it the normal distribution. So just scrolling down a little bit, you can estimate the standard deviation from the graph of the normal distribution. We don't really need to do that, but it's a nice little thing to be able to see. And if you take a look over at this point that I've just drawn in, what you're looking for is we're going to look for the 2 points. There's one on each side. 2 points on the curve where the curvature goes from concave up, and basically you're looking at the curve sort of is like this, where if you were to put water in it, it's shaped kind of like a bowl. And so, for example, this little right-hand side over here that I've highlighted is shaped in that way, that it's concave up. And then it changes at that point to concave down, where if you tried to put water in it, it would simply run out. So it goes from happy face to frowny face. And you can see that on the other side, there's similarly a position where it's going from concave down to concave up again. And it turns out that this distance here, let me write a little bit lower so that it's nice and clear. This distance here, and similarly on the other side, is one standard deviation. And I think you can see that the majority of your points are going to be within that. Empirical rule says it's going to be about 68% is going to be within one standard deviation from the mean. We're going to refine that a little bit later. So once again, the parts of the graph that are concave up, I've highlighted in yellow, and the part of the graph that's concave down, I've highlighted in blue here, so you can kind of see what's going on. Okay, well, what's the shape of this graph? This part is not strictly necessary, but I feel that I should mention it for completeness. So digression will not be tested. And if you don't like scary looking equations, then I advise you to turn away for a couple seconds or skip forward. But I'm going to write out the equations. What is the shape? It's given by the formula y is equal to 1 over sigma. Remember, sigma is the standard deviation times the square root of 2 pi. That's a little normalizing factor to make sure that the area under the curve is equal to 1. And then e to the complicated exponent coming up, negative x minus mu, where mu is the mean, all squared divided by 2 sigma squared for negative infinity less than x less than infinity. But in this class, we don't need to know that, so we're never going to refer to that again. So it's a probability density curve. So the probability the total area under the curve is equal to 1, and the probability of the data point, x, being between values a and b, is equal to the area under the curve between points A and B. And if it's a little hard to visualize, that's okay. We're going to draw a little graph here. Actually, my curves are looking pretty bell-shaped today, so that's kind of nice. Let's say that here's point A, and here's point B, and we're graphing x on the x-axis, and we're not worried about the y-axis. But if we were to then highlight this little area here, which is the area underneath the curve between points A and B, that is equal to the probability that x is between A and B. Now remember that the entire area under the curve is equal to 1, because the probability that x has some value once you've measured it is 100%, but the probability of being between certain values, you basically calculate the area. So, of course, the question then becomes, but how do you do that? How do you calculate this area? Now, for those who have taken calculus, I'm sure that you'd appreciate that this is an integral. The problem is that this integral doesn't yield to our standard integration techniques, and so we have to use other alternatives. One, well, you use some numerical methods, and you use a calculator or a computer, which of course is the preferred option. Some variety of technology. And the way that we did this in this class up until now is we'd look it up in a table of values. Mostly because during a test you wouldn't have access to the kind of calculational tools that you could find on a computer. There are calculators that will do this, but I have not required that students get a calculator with the stats package for this class. So normally I would hand out a set of tables and we'd go from there. For this course, because of the online nature of it due to the COVID crisis, we will use an online calculator and dispense with the table of values. So an online calculator rather than using a table of values. So if you look at the notes and, last year's test and all that sort of thing, you'll see a bunch of calculations that we're just not going to get into because we're going to use online tools instead. Now, I do want to give you just a little bit of context, just in case you're running around the internet looking at examples of this stuff. And so, if using a table, there's a problem. You'd need an infinite number of tables. Because you'd need one for every combination of mu, the mean, and sigma, the standard deviation. And the question is, so what do you do then? You standardize it. Instead of using mu and sigma, you use z is equal to x minus mu over sigma. That's our z-score that we looked at earlier in, I guess it was chapter 2. This is the z-score. And what I'd like you to know is that if you're looking at your textbook or you're looking at solutions from last year and you see a whole bunch of calculations with Z, the reason you're doing that is because you need to do a standardization before you can use a normal table. However, for this class, because we're trying to do things in a slightly different fashion, I'm going to give you an online calculator to use instead. And I think your goal should be to get the same answers as the hand calculations while using a different set of tools.